Welcome everybody to our new seminar. Today it's my pleasure to have here Anthony Lee, who is from the University of Bristol, as we all know, and he will talk about a general perspective of Metropolis-Hastings algorithm. Please, Anthony.
Okay, thank you very much, and apologies for the technical issues. I think at least a lot of it is probably my computer's fault or my fault somehow. This is joint work with Christoph, Andrew, and Sam Livingston, and there's a preprint on arXiv which we will update at some point. It's quite long, so actually I'm just talking about a very specific subset of what we cover there, and in fact we're going to make it probably even longer by adding more examples and obviously fixing some typos and minor mistakes. But if you want to give us feedback on any aspect of it, of course, we'd be very interested to hear. So I'll just talk very quickly, I'll talk about the framework. Basically, I'm not going to talk that much about sort of the main theorem in some respect, because the main theorem in some respect is probably not too surprising, but I think the nice thing is that it's a very sort of constructive way to sort of verify the kind of correctness or the invariance of certain Markov kernels. I think it's sort of, even though you would use it for more complicated Markov kernels, it actually simplifies to some extent the procedure for doing so. And I'll have a brief foray into sort of deterministic proposals and HMC before talking about what is really the main aspect is sort of these three things. So try to work up how you would define appropriate Markov kernels, which involved either random numbers of proposals in some sense, or a random number of random variables that you would actually simulate when you try and simulate from your Markov kernel. And that involves sort of simpler methods. So I'll look at a sort of a random proposal version of the IMH. Not that you would use the algorithm, but just for pedagogical reasons, for example. Then look at sort of Markov chain proposals. So something a bit more complicated than independent proposals. And then finally move on to things like nuts-like kernels, which was a kind of an inspiration for some of this work, because I think it's not so easy to understand line by line some of the proofs of the correctness of the HMC nuts algorithm. So this is some kind of a attempt to make it clearer, at least for some of us. Okay. Okay, so the general idea, and this is like, there's only going to be a couple of slides on this. Hopefully it's not too complicated. The general idea is maybe other people find it nice. The idea is you have some kind of probability measure mu, and it should admit pi, your sort of target probability measure of interest, as a marginal. And you may, for example, identify it with a particular component of psi when psi is distributed according to mu. And we'll just call that psi 0 for the sake of being specific. Okay, and then after you define your mu, you define an involution phi, right? So it should be basically, when composed with itself, be the identity. And then just the last bit of notation, you should we just denote the push forward in a pretty standard way. So nu phi is the push forward of nu by phi. So for example, if you have psi distributed according to mu, then basically phi of psi is distributed according to mu superscript phi. Okay, and then the idea here is that if you were to define a Markov kernel, which basically just tries to swap psi with phi of psi when psi is distributed according to mu, then the acceptance ratio would be given by this expression, which is actually not too difficult to compute in some circumstances. Okay, so basically rho is the density of mu with respect to some reference measure, lambda. We assume that lambda is equivalent to lambda phi. Okay, and then the acceptance ratio should be given by the ratio of the densities, say rho composed with phi at psi and rho of psi, multiplied by some kind of change of measure sort of correction term. Okay, and in many cases, in fact, for the entirety of this talk, I think we can basically ignore this, because you can choose in some circumstances your reference measure lambda such that lambda phi and lambda are the same. Okay, in which case, obviously, you can just ignore this. Okay, but this type of term does appear in certain types of algorithms that people would run, for example, in reversible jump and so on. Okay. Okay. So the basic algorithm that you would actually use is you would combine this sort of mu and this phi with an acceptance function, because acceptance ratio doesn't give you enough, and the standard one that you would choose is sort of the Metropolis acceptance function. But of course, as we had last week a talk about Barker's, there are several different acceptance functions, and in fact, they just need to satisfy a kind of fairly well-known and specific condition to be valid acceptance functions. Okay, so one sort of way to construct a kernel, a sort of useful Markov kernel out of this framework is to say you're at some psi naught. You can sample all of the rest of the components of psi from a conditional distribution under mu, right? And then you can accept sort of phi of psi as your new component, and in particular phi of psi 0, the 0th component of phi of psi, with probability the acceptance function composed with the acceptance ratio at psi. Okay, so that's pretty easy. This covers basically many algorithms that people actually perform. Okay, so one thing you can think of is you can think of this as a cycle of kernels P0, P phi, where P0 fixes psi 0, refreshes psi minus naught, and P phi just attempts to replace psi with phi of psi. Okay, and it just so happens, I mean, it's not obvious from the presentation, maybe for some people, but in fact, the psi naught, the sort of psi naught coordinate of this Markov chain is itself pi reversible. Okay, so it defines even a pi reversible Markov chain. Okay, so just to make things clear, something we all know and love, or some of us love, there's the random walk metropolis. So you could let mu have a density rho of xv, where rho of xv is pi x qv. Okay, and you assume, because you're doing random walk metropolis, that q minus v is equal to qv for all v, being a bit abstract. And then you could consider, this is not the only involution you could consider, but you could consider this involution phi of xv is x plus v and then minus v. Okay, and this satisfies indeed lambda phi is equal to lambda, and phi is indeed an involution, and you obtain from your acceptance ratio rxv is just this ratio here, which you can write out in this manner, and you notice that because of the fact that qv is equal to q minus v, well then you just get the standard Metropolis, random walk Metropolis acceptance ratio. Okay, so that's just a simple example to see how it works in practice, or an example. I'm not going to get at all the things today, obviously, but one of the reasons we think it's nice, a nice way to present things, is that you can just think of mu, phi, and a as a certificate of correctness. Not that other people don't have other ways to provide certificates of correctness, it's just somewhat streamlined. Okay. Okay, so here's an example, just because some people had asked about this one. Also because the proof for this particular Markov kernel is a little bit complicated if you look at the original paper. So here you have some kind of target density for pi, which is given by some prior times some likelihood, or some likelihood with an unknown normalizing constant. Okay, you can't compute z pointwise, so you have to do something clever in order to devise an appropriate Markov kernel. You let psi be phi, phi prime, and x, right? Where basically the density of phi, phi prime, and x is to have theta, theta prime, and x. Don't know what I'm doing there. Rho of theta, theta prime, and x is equal to pi of theta, some kind of proposal for theta prime, and then basically x should be distributed according to the distribution associated with theta prime, with that unknown normalizing constant. Okay, so you can write out the density, and then you consider now this particular involution, theta, theta prime, and x maps to theta prime, theta x. So you're just swapping theta and theta prime, but leaving x the same. Okay, it's obviously an involution. And then you can quickly derive that the acceptance ratio is just given by this particular quantity, which doesn't involve any z theta or z theta prime, and in fact is just exactly the acceptance ratio that is given by the Murray and co-authors paper, okay, known as the exchange algorithm. Okay, so one thing that's nice is I think in the proof in that paper they kind of appeal to some idea of doing this for all kinds of x's. I don't remember all the details, but basically it was a little bit complicated, whereas this is clearly quite straightforward. Okay, and there's other ways you can deal with similar types of algorithms, like the single variable exchange or the single auxiliary variable kernel. Okay, so let's get on to something a little bit more interesting. So it's useful because we want to talk about HMC essentially, that you can easily see how you can construct proposals built from what you might call reversible deterministic mappings. Okay, so for example, one type of deterministic mapping which you might take, which we could call psi xv is equal to x plus v. So you just move in the direction of v and you keep the velocity the same. Okay, and you can consider an involution sigma composed with psi, where sigma xv just basically flips the sign of v. Okay, in some sense, this is interesting because phi is the random walk involution, right? So it's easy to verify that p phi is mu reversible just because it was the same as in the random walk case. But if you look at sort of p psi, which you can think of also as p phi p sigma, you can see that it's mu invariant but not mu reversible. Okay, so the idea is what you'll do is you'll perform an accept reject move. Say, like if you're at xv, you'll perform an accept reject to see whether you should move to x plus v minus v, which you could call, well, basically you'll call whether or not you accept or reject it, you can call it x prime and v prime, and then you'll always flip x prime v prime to x prime minus v prime, right? But what you can see is that if you had accepted, you basically move to x plus vv, and if you reject, you move to x minus v. Okay, and this is sort of the guided random walk of Gustafsson in a 1998 paper, which is also related to several other non-reversible algorithms that are cited there. Okay, so that's just one example of using a deterministic mapping. In some sense, it's quite related to what people actually use with Hamiltonian Monte Carlo or hybrid Monte Carlo. Here you have rho being, again, like pi of x and kappa times v, say, and you have some kind of sophisticated leapfrog mapping, which we won't get really into the details of. Psi is like the composition of three particular sort of different psis, and they satisfy this kind of condition. Okay, and you can consider an involution phi being sigma composed with this this particular mapping like L times. Okay, and sigma is exactly as before. You flip the sign of v. Okay, so it's clear from actually the definition of psi A and psi B that psi is volume preserving. Okay, which means Lebesgue preserving basically in here, and you can show that it's reversible in the sense that well, if you have this condition, which is obviously satisfied for the actual leapfrog mapping that people use for HMC. Okay, and then you can see that in fact the acceptance ratio is just given by the ratio of the densities at x and b. Okay. There are other things, like there's other ways you can think about deriving the acceptance ratio, but maybe I won't go into all of those details, especially because we missed a bit of time at the beginning. I think the important thing for some of this talk is that somehow in practice, it's not obvious how people should set the number of steps. L, which is part of the motivation of the sort of no U-turn sampler. It's also worth noting that the proof of validity in some sense says nothing about whether the algorithm is actually good. So one thing you can see is that if I look at this, like there's lots of types of sort of J's and I's which you could use, and the J's that satisfy this, and you know exactly the same argument would show that those are valid algorithms, right? being Lebesgue preserving is not necessarily saying that you're going to have a useful algorithm. Okay, so if you wanted to understand why HMC itself is good, this type of argument wouldn't help. But if you want to see why HMC leaves pi invariant, then of course this is doing the job. Okay. Okay, so let's just talk about maybe, because we want to build up to nuts, the no U-turn sampler, we can try and build up using some simpler examples. So things we know and love are the independence Metropolis-Hastings algorithm. But let's imagine that we're in some kind of hard problem, and for some reason we think it's a good idea to use multiple proposals rather than only one proposal for our independent sampler. So I'm not saying it's a good idea, I'm just saying, like, let's try it. Let's just think about it for fun. Okay, so this is a multi-proposal IMH, and let's let psi be nzk, where this z is a sequence z0, z1, z2, and so on, where z0 is distributed according to pi, and z1, z2, and so on is an infinite sequence of new distributed random variables. Okay, let's let var pi be d pi by d nu, and then let's imagine that we're going to set some kind of stopping time, tau of z to be the infimum of n greater than or equal to 1, such that some Sn of z is equal to 1. Okay, where you choose some SIs you choose your SIs to be some particular functions that are valued in 0, 1. Okay, so we can already see that we're building up some kind of, we just simulate lots of z's from nu independently, and basically we're going to have some sort of n is equal to tau of z telling us how many we might actually consider. Okay, well, that's how we'll use tau of z. Okay, so once we've got tau of z, which we call n, we'll simulate k from some categorical distribution supported on 0 to n, right? And depending on the values of z, but probably only on the 0 to nth values to be useful in practice. Okay, and then we can consider this kind of involution. Phi of nzk is going to give us a sort of new, tau composed with sigma k of z. We're going to, the reason for that is we're going to basically apply sigma k to z as well, and we're going to have k at the end. And sigma k is going to be something that basically just swaps the 0th and kth components of z. Okay, and because it's a swap, it's clearly going to be an involution. Okay, does that make sense? At least this is all we need to write down in some sense. We've written down basically what mu and phi is. So at that point, we can start to think, what is the acceptance ratio going to be? Well, the involution phi is going to preserve lambda, which is basically 2 counting measures and nu infinity. And the acceptance ratio is therefore not too difficult to work out. You basically work out what is this ratio. Well, I'm going to get var pi at zk divided by var pi at z0 multiplied by, well, a ratio of the probabilities of choosing that particular k under the 2 different sequences. Okay, and remember those sequences are almost the same except that 0 and k have been, z0 and zk have been swapped. Okay. And so if you were to choose, for example, I mean, you could choose whatever you like, right? But if you were to choose this var sigma k and z to be proportional to var pi of zk, multiplied by the indicator that k is in 0 to n, then you'll get quite a nice acceptance ratio, right? In the sense that it will be just given by the ratio of those densities multiplied by whether k is between 0 and the minimum of n and n prime. Okay, so I guess one thing that could happen that would not be good is if k was bigger than n prime, then you would definitely reject. Okay, so I hope that makes sense. It's just sort of a way to see there's no problem in sort of imagining that you simulate an arbitrary number of proposals. You can still work out nicely what the acceptance ratio will be. Okay, and of course in practice, you don't actually simulate from mu, you just simulate enough of mu to enable you to calculate the acceptance ratio, or more generally enough to actually flip an alpha coin where alpha is the acceptance ratio, the acceptance probability. Okay. Okay, so one thing that's maybe not so great about that particular approach is that, there was this question like, well, what if when I swap them, when I swap Z0 and ZK, it's definitely possible that N prime may be quite different from N, right? And certainly there's no reason for them to be equal. Okay, but you can come up with sufficient conditions which basically tell you when, which can tell you some instances in which N prime will be equal to N. So basically the stopping time associated with the two sequences will be exactly the same. So one set of such conditions is the following. You could impose a condition. These are conditions basically on the SI, S1, S2, and so on. You can impose the condition that SK of Z is non-decreasing in K, right? You can also impose the condition that SK of Z should be equal to SK of sort of sigma L of Z. So that's where you swap the Lth and the 0th component of Z. They should be the same for all L in 1 to K. Okay, and then you can impose, this is a bit interesting, you impose the condition that your categorical distribution actually shouldn't be supported on 0 to N, but should be supported on 0 to N minus 1. Okay, so for example, one sort of set of stopping functions that will satisfy this is if you were to set Sk of Z to be the indicator that the sum of the densities up to time K exceeds C for some constant C. Okay? Because in that case, you know that N and N prime will be the same, which also means that if we just go back, we know that basically this will be exactly the same sum. This will be 1, so you're going to get an acceptance ratio of 1. Okay? So an example of a function that doesn't satisfy this criteria would be the effective sample size. So if you thought you were going to be clever and you thought, oh, I don't want to look at the sum of the densities, I want to look at sort of some kind of natural measure of the effective sample size, then it's not necessarily the case. Well, it's not the case that it satisfies these conditions. And in fact, it's possible for N and N prime to be quite different. Okay, so the high level idea, at least for some of these conditions, is that if you pick your function well, then doing swaps before you stop, as in, before time N, cannot affect whether or not you will actually stop, or it cannot affect when you will actually stop. Okay, so that's quite simple. And again, it's just the IMH. There's no actual, I think, strong reason why you would actually implement that algorithm, but it's sort of simpler because of the independence. So now we can think of something that's slightly more complicated, where instead we imagine that our sort of Z, this kind of capital Z sequence, is going to be a Markov chain. Okay, so we consider a two-sided Markov chain, K, pi, Q, and Q star, where Q and Q star will be sort of time reversals of each other. And we're going to have the condition where basically ZK is distributed according to pi, right? And then to the right, we will simulate the components of Z using Q, right, which is some Markov kernel. And then to the left, right, we will simulate using Q star, right? So that basically it just looks like a shifted version of a Markov chain, except that Q is not necessarily pi invariant. Q is just invariant with respect to nu, say. Okay. Okay. So one can show that even though these are sort of Markov chains, that there are Radon-Nikodym derivatives, at least on certain subsets between the two measures, given by the ratio of the densities var pi of zk divided by var pi of z0, where as before, var pi is the Radon-Nikodym derivative between pi and nu. Okay, and of course you just have to make sure you're only on a specific set, which you can basically, if you simulate things that are not in a set, you basically just throw them away. Okay. So the idea for a kernel that you might use in this particular context is at Z0. I don't know if I went too fast, but basically here this superscript k and the superscript 0 is talking about sort of the Radon-Nikodym derivative between the measures associated with the kth component being distributed according to pi and the 0th component being distributed according to pi, right? Okay, and hopefully the reason for that will become clear, because our idea for a kernel is that our psi will be Z and K. Z is the sequence, right? And Z0 will be distributed according to pi at stationarity or under mu, right? And we will just, given Z0, we will simulate our Markov chain forwards and backwards. Obviously, we won't simulate the whole thing. We'll just simulate sort of a suitable amount of it, right? And then we'll sample K according to some probability. And we will consider this involution, Zk maps to the shift of Z, Z shifted K times and minus K. So this will also be an involution. And then we can see that the acceptance ratio is just given by this particular quantity. And of course, in general, you may not be able to calculate it depending on how complicated var sigma is. But if you choose var sigma in a suitable way, you may be able to calculate it in finite time. Okay, so one thing which you might do is that you could choose, just for example, var sigma of I given Z to be proportional to the density at Zi, multiplied by I being in some window around 0. Okay, and if you were to do that, then you'll obtain an acceptance ratio, which is basically the ratio of the sums of the densities, where where basically you're looking at the ratio between minus tau and tau in the numerator, and in the denominator you have this sort of shifted ratio, right? So you're going to have to simulate sort of a certain amount of the Markov chain first between minus tau and tau, and then depending on K, you'll have to simulate a little bit more to the right or a little bit more to the left, right? And then you'll have to compare a ratio that is not necessarily 1. Okay, in some sense, this is a bit similar to before. The windows are not the same. There are ways to try and make the windows the same, which again, this is related to how nuts actually works, right? So to make the windows the same, what you can do is you can randomize the endpoints. Instead of some fixed tau, maybe tau is a poor choice of letter, but because it was just a fixed number. To make the windows the same, let's randomize the endpoints. Let's let psi be ZLK, where instead of just looking at a fixed window, we're going to simulate L from a uniform on 0 to m-1, right, to define a sort of window between minus L and R, where R is, m-1 minus L. Basically, you want to have a size m window, and you kind of offset it by a certain amount that's uniformly drawn. Okay, and then you can define a different involution. Okay, and then what you can see is that the interesting thing about this part of the involution, right, L plus K, is that it works to make the sort of random shift sort of compatible once you apply the transformation, in the sense that basically the windows will coincide. Okay. And this is basically a typo. That's a typo. You should obviously choose it to be between minus L and R, right? Okay, so hopefully that's somewhat clear. And then we can now finally start to think about the nuts algorithm, which, as you remember, was motivated by this idea, which was, say we want to run HMC. I'm guessing that people are somewhat familiar with HMC. HMC is sort of a nice, it's a nice, at least when used in Markov chains, well, at least normally used in Markov chains, for example, in Stan, it's a discrete time sort of proposal where it can be very close to being pi invariant. So you hope that you can accept the proposal with a fairly high probability, but also that your proposal may take you to interesting places that are not super local to where the current point is. But the big question, at least for some people, it's a natural question, is sort of how many steps of this sort of discrete time algorithm should you use to define your actual proposal? Okay, and so what's done in this paper is they make the observation, which is again also quite natural, is that maybe it's a good idea to stop sort of simulating this sort of this proposal or this sequence once the trajectory starts turning back on itself, because if it was like a nice ellipse or something, then it's kind of, you've probably gone as far as you're going to go. There's no point going further. Okay. So they have an idea that a good, that a good idea would be to stop when this condition is met, which, it may not make perfect sense when you look at it like that, but it basically corresponds to checking when you're turning back on yourself. Okay. So for simplicity, we'll just consider a simple version, which is also what they consider as the simple version of the NUTS algorithm in that paper. My understanding is NUTS has gone further since then, so I'm not saying I'm explaining what they're doing in actual STAN, but more like the kind of the original paper. So the target is going to be some kind of sliced version of the original target. So pi of u given z is going to be the indicator that u is less than or equal to var pi of z, where u will have been drawn from some drawn uniformly. Okay, between 0 and var pi of z naught. And the doubly infinite Markov chain that we will consider is basically, it's going to be a deterministic sort of Markov chain. So it's a bit, maybe not really a Markov chain, but it fits within the same framework. So Q of Z will be basically moving you forward according to like one leapfrog step. And Q star will be moving you backwards according to, the same kind of leapfrog step, but backwards in time, which basically involves flipping the velocity. Okay. So how do we define and verify a correct kernel that tries to implement this kind of idea of sort of not turning back on itself? And clearly there's sort of a random number of, you're trying to think of a situation where you're going to apply this leapfrog mapping a kind of random number of times. Okay, so just in case it's not obvious, the kind of, and just to look at notation, the idea is that if you were here, and this was your sort of leapfrog mapping, moving you around, then maybe you want to stop when you're around here or something like that, right? When you're not getting closer, when your left point is not getting closer to your right point, say, or something like that, right? But in practice, we'll actually do it sort of in a double-sided thing, right? So we'll actually go this way and this way or something like that. Okay. But just for notation, the point is that we'll have Z naught, and we'll just think of everything on a line because there's no reason not to. It only makes things more complicated if you try and look at the actual space on which the points live. Really, you have some Z0, Z1 up to ZR, Z minus 1 up to Z minus L. And that's kind of sufficient. Okay, so for our for what we're talking about, in some sense, what I'm, the actual reasoning is not specific to NUTS. It can actually be used for all sorts of different types of schemes that have the same flavor. So in particular, it doesn't matter whether Q or Q star are deterministic or truly stochastic Markov kernels and so on, right? They can be, it just needs to be a K, pi, Q, Q star Markov chain. Although I'll use the slice sampling thing just to simplify presentation as well. Okay, and we'll consider windows of states that are defined around Z0 corresponding to some Bernoulli random variables. So some Bernoulli half random variables at each time, and you can think of a different sort of window, and that window just depends on these Bernoullis in a fairly simple way. So if Bn is equal to 1, then you're going to extend your window by moving to the left. Okay, and if Bn is 0, you're going to extend your window by moving to the right. But the way you do it is that when at time n, if you extend the window, you will add 2 to the n minus 1 points. Okay, so you're kind of doubling, you're doing a sort of doubling thing, right? Which it makes some sense because you're trying to, quickly find the right kind of window to be looking at. Okay, but the other nice thing is that the total size of the nth window is always 2 to the n, because you're always just adding points to your window. Okay, and in terms of what I talked about earlier, one thing you can notice is that this is actually like marginally sampling ln from a uniform on 0 to 2n minus 1. Okay, and also you can think that b1 to n is in fact a kind of reversed binary representation of ln. Okay, the only reason for that is to notice that there's a one-to-one mapping, right, between the b's and the l's. Okay, so so far so good, but really one thing that's interesting is that you're going to choose to stop exactly the same way as we kind of did before. You're going to choose to stop by choosing some stopping time that depends on basically some functions Sn and basically your Markov chain and your Bernoullis. Okay, so we don't need to get into the details of everything. In particular, this notation is maybe it's just a bit annoying. If we're honest, let's just define mn of b to be the midpoint of the window from minus ln to rn. So it basically splits the window into two pieces. Okay, and then let's define. I mean, I'm sure there are lots of other ways you can define stopping functions. In fact, you can always define them however you like, but we want to accomplish a particular purpose here. So here we're going to define our stopping functions in this way. For some function, for some functions f, we're going to, which I'll define in a second, Sn of zb is going to be sort of fn minus 1 of sort of z. It's going to be fn minus 1 applied to like the left window, or fn minus 1 applied to the right window. Okay? And these f's are going to be defined themselves in a bit of a funny way. To define fk of sort of some 2 to the k points, you're going to apply gk to those points to see whether or not that rings a bell, right? 0 or 1, or basically whether or not fk minus 1 applies to the left sub window of that particular 2 to the k input as well, and fk minus 1 applied to the right sort of sub window or sub tree of points. Okay, and if k is 0, then you just apply this g0. So in some sense, this is just a funny way of using some functions g which encode conditions for stopping, right? But basically, you split it all up into a nice tree for a particular reason, which is to ensure that a particular condition will hold. Okay, I hope that kind of makes sense. Before we look at why that's a good idea, we can basically look at, well, what will you do once you stop? So these conditions define when you should stop, right? You're going to stop as soon as like a bell, as soon as one of these GKs is 1, and then it makes basically everything 1, right? Okay, so we're going to stop at some time n, and because, for example, say we're in the slice sampling setting, we're going to just sample k sort of uniformly on the slice, but associated with the window up to time n minus 1. So again, we don't consider the sort of window that caused the bell to ring in some sense, right? We only consider the window from the previous time. Okay. So we look at k being, say, uniformly distributed on that window, but such that it's in the slice. So u has to be less than or equal to var pi of zk. Okay, and then you can define an appropriate involution. Again, you're sort of shifting your Markov chain to define your involution. Here, we're going to have the same stopping time, which involves us actually showing that has to make sense. And then you're going to modify your Bernoullis in a particular way, which is similar to what we did with trying to make the windows the same with the Markov chain proposals. You're just trying to make sure that everything is consistent. Okay, and then minus k, which makes sense given the shift. Okay, and the claim, I'm not going to go into every detail, but the claim is that the acceptance ratio will be 1. Okay, and here I just have some of the things I already said. So basically, the choice of chi n minus 1k is basically to make sure that the same window is essentially being used after you perform the mapping in order to define when you stop. Okay, and also which points you actually might sample. Okay. Okay, so we can look at a picture, but indeed, one of the main things that's outstanding is to check that really the stopping time should be the same. But here's a sort of picture for trying to understand maybe chi n minus 1k. So if you imagine that, n is going to be 4, we simulate 4 Bernoullis. First one is 0, so we move 1 to the right, right? So we simulate Z1. Second one is 1, so we simulate 2 times to the left. Third one is 1, so we simulate 4 times to the left. And the last one is 0, so we simulate 8 times to the right. Okay, and then we imagine that we've chosen k. Once we've done that, imagine we've stopped. We've chosen k to be minus 4. We can only choose between these guys, because remember, we ignore the last bit of the window. So we choose k to be minus 4, which is this guy, And then we can try and see, well, what should be the corresponding sequence of Bernoullis that you would like if you want to make the windows sort of match up at time n-1 and time n, say. Okay, and to do that, well, here we have 2 points to the left, right? So we know that there's only one Bernoulli sequence of size 4 that's going to give us just 2 points to the left, and that's going to be the one where the second Bernoulli is going to be 1, right? So basically we know it's going to be 0, we're going to move 1 to the right, 1, 2 points to the left, and then, 4 points, and then 8 points. Okay, so basically this is just showing that, indeed there's a nice just one-to-one mapping between what B prime should be given what B is and what the window is. Okay, so hopefully that clarifies some things. And then here we can see, here's an attempt to like very quickly explain why for any sort of ZB, we're going to have the same stopping time, right? After we sort of apply the transformation or apply the involution. Okay, and sort of one thing that you can see, I won't go into all the details obviously, is that this will satisfy the condition that Sn of ZB will always be greater than or equal to Sn minus 1 of ZB. This is like that kind of, I think before we had a condition which was like Sk was increasing in K. This is like the same kind of condition, right? And the reason this works is because of those recursive checks on the binary tree. Okay, because it kind of says no matter how I got to where I was going, I will have made all of those checks. And if I had stopped earlier, it would sort of contradict the fact that I've only now stopped. Something, okay, I can't get into all the details too easily. It's actually not too complicated, but it's that's how it works. And the second point, which is more minor, but only for implementation details, is that Sn of ZB is of course greater than or equal to Gn minus 1 of the which is basically associated with one of the windows that was before, or the actual window that came before. Okay, and so this first one is sort of sufficient to tell you that in fact, if tau psi was equal to n, then tau of phi psi will also be equal to n, right? Because if tau psi is equal to n, then Sn minus 1 of ZB has to be 0, which means that Sn minus 1 Z prime B prime also has to be 0. Okay, and if tau psi is equal to n, they both have to be equal to 1 because they're basically the same windows. That's how the sort of chi works, right? At time n minus 1 and time n, you're looking at exactly the same points. Okay? Which also explains why you have to kind of ignore the points that come from the bit of the window introduced at time n. Okay, so the second point, I mean, you don't need to get into it. It just sort of allows you to stop earlier at some point, because as soon as you see that sort of this G rings the bell, if you were to see that this G rings the bell, then you can know that basically at the next time you will stop. So, there's no point simulating that bit of the window. Okay, so I think I'm running out of time, and I've said most of I think what is worth saying. Of course, in practice in nuts, you pick the GKs in a particular way. I think I've indicated before. The idea is that you pick the GKs when they tell you that sort of some component of your window is sort of turning back on itself. Okay, and so that's exactly how these conditions work. Or this is what's encoded here. And for G0, they have another condition which just basically tells you whether or not your leapfrog integrator has sort of become very unstable. So basically G0 of Z will ring the bell if sort of the log density is much smaller than the log U associated with your slice. Okay, and typically this will be quite large. So it typically means that your density has really gotten tiny, right, in a way that indicates that there's no hope for your sampler at that point. Okay, there's many variations, there's many other things you can do. I think one thing that's also interesting is there's nothing actually specific in what has been talked about here that says that Q and Q star should be sort of these deterministic or degenerate kind of kernels, right? You can make them random if you like, if you have a good way of coming up with interesting stopping rules. Okay, so in summary, I mean, I think it's kind of fun to think about random numbers of proposals or interesting and creative ways to try and come up with new Markov chains. The sort of this mu phi sort of perspective, it's more to help you verify that your algorithms are correct, although of course it also has a role in sort of designing them, because you can use it as a sort of way to easily check whether your algorithm makes sense. Like, what will your ratios look like? But it's no substitute, obviously, for actually having good ways to come up with good Markov kernels. Okay, and I think one of the things that we think at least is nice about it is just that it's very mechanical, right? You just go, you say what's mu, what's phi, what is r, figure it out, and see what it might mean for your Markov kernels. Okay, and one thing that it does definitely do, which I think was not so easy to do using, I mean, I'm not saying it's impossible. I'm sure there's clever things people can do, but it sort of streamlines the kind of process by which you can verify whether Markov kernels involving lots of auxiliary variables and randomness are actually correct. Okay, thank you.